In this lecture, I want to complete the discussion of the choice of production function application of model selection, and then to discuss simultaneous confidence intervals and Bonferroni intervals. That will then leave me the remaining 4 lectures clear to discuss model selection in time series contexts, which I intend to leave the beginning of that until the next lecture. The production function example was a problem where we had a collection of production functions, and we were interested in hypotheses, first of all, about the elasticities of substitution between 3 factors: employment of people, the hours of work, and capital stock. And the second set of hypotheses concerned the error structure on the production functions, and in particular whether it was an additive error or a multiplicative error. And finally, there was the hypothesis concerning constant returns to scale. Are there in fact constant returns to scale in the production function? If there are, then the parameter in almost all the functions nu would be equal to unity. The hypotheses involved within the set concerned with the elasticities of substitution are very large in number. They are not uniquely ordered, and so I was proposing last week that we use the exhaustive search procedure of ordering the hypotheses on the elasticity of substitution into all possible orderings that make sense economically, and then using the optimal Anderson sequential testing procedure within each of those ordered nests. But in considering that first, it means we've taken some other decisions about the relationship between the hypotheses concerned with returns to scale and error structure in relation to those concerned with the elasticity of substitution. If we look at these 3 sets of hypotheses, we can see from the beginning that the hypothesis about constant returns to scale is not independent of the choice of error structure, neither is it independent of the choice of form for the elasticities of substitution. Equally, the hypotheses about the error structure are not necessarily independent of the form of the elasticities of substitution. As set up so far, we don't have any unique ordering on the hypotheses concerned with returns to scale, those with the error structure and those with the elasticity of substitution. So that at this point, I impose some structure on the problem by introducing an arbitrary ordering and saying that hypotheses concerned with the returns to scale will be considered last. In other words, we'll take our decisions on the elasticity of substitution and on the error structure, and only then consider whether there are constant returns to scale. So that we've put an ordering on saying that 3 comes last. We're only interested in that once we've taken decisions on sigma ij and the error structure. And we also have ordering in the sense that I say that I'll only consider hypotheses about the error structure once I've determined what the elasticities of substitution are. So that to tackle this problem, I have imposed arbitrary ordering on the sets of hypotheses. So that we have now a set which we can denote by H1, we have a set which we can denote by H2, and a set of hypotheses we can denote by H3, and we're now saying that these are ordered. But the ordering has been imposed by the person conducting the investigation. It wasn't a natural ordering. Well, having done that, we concentrate on the first set of hypotheses, those concerned with the elasticities of substitution. And as I indicated last week, the procedure here was to consider all possibleness and all possible orderings within those maintained hypotheses from the 9 functional forms that I considered. So that we had the Sarto 2-level CES production function as one maintained hypothesis. The Mukherjee variable elasticity of substitution production function, but with a constant ratio of elasticities of substitution production function as a second maintained hypothesis. And then finally, the simple CES function, just to complete the set of functions. Within each of these maintained, I then had a series of nests. The ordering here is not going to agree with the numbering here is not going to agree with the numbering last week. I simply want to illustrate the points this week. If in fact we only had 7 nests, and we had 4 within the Sato function, then N5 and N6 come up within the Mukherjee function, and finally N7 within the simple. Then each of these nests consists of a sequence of ordered functional forms, which is the same thing as saying that each of these nests consists of a sequence of ordered hypotheses. And within each of those, we perform the Anderson optimal sequential testing procedure. Well, an important point to consider in performing that optimal sequential testing is what level of significance should we use for each of those significance tests. Well, if we look at the nests that are available within each of these maintained hypotheses, the sequence of hypotheses is never more than 4. In other words, there are never more than 4 functional forms in any one nest. So at most, we're going to perform a sequence of 4 significance tests. Given that we're using the Anderson procedure, we know that the test statistics in that sequence, when performed in the right order, are statistically independent. So if we now want to look at the size or the probability of type 1 error for applying the procedure in any one nest, then that's going to be determined by 1 minus alpha, where that is the size of the test we're performing, which last week I showed was equal to 1 minus the product of 1 minus the significance levels used for each of the individual tests, the epsilon i's. And for this particular application, there are never more than 4 tests. So if we have some idea as to what level of significance we want for the overall test, in particular, if we wanted alpha to be at the conventional level of 5%, then that enables us to choose the epsilon i's, the significance levels for each of the individual tests. But we have to introduce more structure yet to get a solution for each of those epsilon i's. In my application, I chose the simple specialization, which is to set each of the epsilons equal to a common significance level. So that we can now solve this relationship using alpha at 0.05 and all the epsilons to be a common epsilon for that common epsilon. If you do solve that, epsilon is 0.0128 to 3 places. So if we want to ensure that the significance level for the test as a whole within each nest is approximately 5%, then we should be doing each individual significance test at something like 1% in this case. And that's exactly what I did in the application. I used 1% critical values for all the test statistics within the sequence, which will then approximately give me 5% overall. Also last week I mentioned that the test statistics that we used to perform the optimal sequential testing were corrected for small samples, or corrected for degrees of freedom. And in particular, most of the test statistics were using the result that minus twice the log of the likelihood ratio is asymptotically distributed as a chi-squared with degrees of freedom equal to the number of restrictions involved in moving from the unrestricted model to the restricted. And that is only valid asymptotically. And the adjustment that I used to these test statistics in practice was to use minus 2m upon t log lambda, where m is equal to t minus k minus 1 plus r upon 2, when capital T is still the sample size, k is the number of parameters estimated in the unrestricted model, and r is still the number of restrictions involved in moving from the unrestricted to the restricted model. The justification for that type of adjustment comes by analogy and not rigorously with the results derived by Box in 1949 in an article in the Journal of the Royal Statistical Society, where he considered the likelihood ratio test in the context of linear models, multivariate linear models with linear restrictions. And he was able to show that this test statistic derived as a function of the likelihood ratio ignores terms of order 1 upon t, whereas if you modify the statistic into that form, this is now ignoring terms of order 1 upon t squared. So it's slightly more accurate. However, for almost all the hypotheses that I'm testing in these nests, the regression models are nonlinear regression models. And it hasn't been demonstrated theoretically that this is a valid adjustment. As I said earlier, I did this using it as an analogy with the results that Box derived for the linear regression model. But notice what effect this adjustment has. It means that the critical values that we're going to use for the test statistics become larger for the modified test, because this test statistic is still asymptotically chi-squared with r degrees of freedom. We're still going to use the critical values from the chi-squared with r degrees of freedom at the same significance level. But now our modified statistic is smaller than the unmodified statistic. In other words, we're going to reject hypotheses less frequently with the modified statistic than we would do with the usual asymptotic form of the statistic. And that's why we can say that by using the modified statistic, we are correcting for the overfitting of highly parameterized models in small samples. So that this modified statistic is more favorable towards restricted models than the unrestricted. So those are the form of the test statistics. I did, in fact, also use pseudo F statistics, so that for any one nonlinear regression model, we could compute the residual sum of squares for the restricted model, subtract from that the residual sum of squares for the unrestricted model, divide by the residual sum of squares for the unrestricted, which is now the proportional increase in the residual sum of squares as we impose the restrictions. Adjust that for degrees of freedom and use the critical values from the F distribution with R and T minus K degrees of freedom. Again, this is derived by analogy with the linear model. This statistic has not been proved for nonlinear regression models to have the F distribution on the null hypothesis. However, some work on statistics of this form for nonlinear regression models has been done by Gallant in Journal of Econometrics in 1975. And he's shown via Monte Carlo that using this test statistic, we do get quite powerful tests of hypotheses in nonlinear regression models. These two test statistics are derived on the likelihood ratio testing principle. As I previously mentioned, we could perform these test statistics using the Wald principle or alternatively the Lagrange multiplier principle. In this particular application, I didn't use any Lagrange multiplier based test statistics, but for some simple hypotheses, I did use the Wald principle. In particular, when any of the hypotheses were of the form H0, an individual parameter is equal to 0, or alternatively, an individual parameter should be equal to another particular parameter we're estimating, then these hypotheses can be tested using asymptotic t-ratios. If there were linear models, then there would be t-ratios. In this nonlinear regression context, you can use asymptotic t-ratios for those. So we only estimate the unrestricted model and then perform a test of these hypotheses using the Wald test principle. For those test statistics, again to correct for the small sample biases or the degrees of freedom, though for the nonlinear regression model, the test statistics of the form of the t statistic are only asymptotically t, in other words, asymptotically standard normal. I have, in the application, used degrees of freedom corrections so that I've used the t critical values from the t distribution at t minus k degrees of freedom, rather than infinity, which would be the standard normal. And that has exactly the same effect as the modification to the likelihood ratio test statistic, namely that you will reject the restrictions less often. So that's the structure of the testing at this first stage. These are the test statistics that I used, and we then come up with a preferred model in each of these nests. At that stage, we then have to choose between those preferred models. In the particular application, that was a very simple choice because the models that were chosen within each nest were in fact all ordered, as far as our preferences are concerned, by previous tests. So that once we'd got the set of preferred models from each of the nests, it was absolutely clear which was the overall preferred model. But notice at this stage, because the hypotheses about the error structure, whether the error should be additive or multiplicative, are only being considered once we've decided on the form of the production function, all these tests had to be performed for both the additive error specification and the multiplicative error specification. So that in the table I had on the board last week, every functional form had a lambda afterwards, and that denotes the lambda of the Box and Cox transformation. And when lambda is equal to 0, then the multiplicative error specification is the one that's being modeled. When lambda equals unity, then it's the additive error specification. So the table last week can be read as the whole set of nests and functional forms for both additive and multiplicative error specifications when you allow lambda to be both unity and 0. So when we've now chosen for the additive error specification an overall preferred functional form, in other words, the best representation we can find for the elasticities of substitution, and also for the multiplicative error specification got the best functional form, we now have to choose between the additive and the multiplicative error specification. Those hypotheses are, as we've seen previously, nested within a general model, and the general model is the model of the Box and Cox transformation. So that if I'd wanted to make the estimation problem even more difficult than it already was, I could have simultaneously estimated lambda in addition to all the other parameters of the functions, and then tested the hypotheses that lambda is equal to 0 and that lambda is equal to 1. However, what I preferred to do was only to consider the two extreme values for lambda, 0 and 1, and estimate the models corresponding to those, namely the functional forms with multiplicative error, the functional forms with additive error, and then to choose the error specification on the basis of the likelihood ratio. So we take the value of the likelihood for multiplicative error specification and the preferred model from all the models, in other words, from all the different types of elasticity of substitution, but with multiplicative errors relative to the preferred model's likelihood value for additive error. And at that stage, if that ratio were greater than 1, choose the model with multiplicative errors, or if it's less than 1, choose the model with additive error. In fact, in the application, I took the log of that, so the critical value is 0. If the ratio is positive, prefer the multiplicative error. If the ratio is negative, prefer the additive error. But that particular criterion, notice that it's not a test statistic, it's just a decision criterion, has the possible problem that the preferred model with the multiplicative error specification may well have many more parameters than the preferred model with the additive error specification, or vice versa. And we know that by increasing the number of parameters in any model, we can, in the end, increase the value of the likelihood function. So that this criterion doesn't penalize over-parameterization. So that if in fact the preferred model for the multiplicative error specification did have many more parameters than the preferred model for the additive error specification, then we ought to take that into account and use a modification of that decision criterion. In my application, the numbers of parameters didn't differ very greatly. However, I did compute Akaiki's information criterion, AIC, which does allow for the different number of parameters in the different models and penalize over-parameterization. So at this stage, we've now chosen a preferred functional form in terms of both the error specification and the properties of substitution between the factors of production. The only thing that remains is to decide whether or not there are constant returns to scale. And at this stage, we now have a single preferred functional form. And all we need to do is to test at that stage whether or not the parameter nu is equal to unity. So that's a very simple test to perform at the end. Well, for my particular application, what happened? Well, first of all, I should mention what the data was. It was cross-section data for 24 industries in Britain. And the data is taken from the Stone Project Programme for Growth. And so the assumption here in looking for a preferred model is that we can find a single form for the production function which is common to 24 industries, which is in fact a very extreme assumption. If the cross-section had been firms within an individual industry, it would have been more reasonable. But this particular cross-section was a cross-section of 24 industries, which could have very different technological possibilities. In particular, very different elasticities of substitution. And yet, in this exercise, we have to assume that the elasticity of substitution is common to all of those industries. However, as a result of that, and because the industries may well represent a very wide spectrum of capital intensity, so that some of the industries may be highly capital intensive and others highly labor intensive, we might well expect the resulting elasticities of substitution to be non-negligible, quite large, just to represent the different techniques of production that have been used in the different industries. Where in fact, the estimates of the elasticity of substitution were all unity. In other words, the preferred functional form was Cobb-Douglas. But for the additive error specification, the Cobb-Douglas function had n, k, and h as separate factors of production. In other words, we couldn't take together n and h and form man-hours as a labour variable. We rejected that particular restriction for the additive error specification. For the multiplicative error specification, then it was Cobb-Douglas with man-hours as the labour variable, but capitals and capital stock as the other variable. Both each had constant returns to scale. When I came to perform these tests to discriminate between the multiplicative and additive error specifications, I found that in moving from the likelihood ratio criterion to Akaiki's information criterion, I often changed the decision, despite the fact that the number of parameters, the difference in the number of parameters was only one, which should suggest that there are some possible problems. And the problem, I believe, is that this particular data set is really not sufficiently informative to be able to distinguish between all of these different hypotheses. We're asking far too much of that data set to choose among all those hypotheses. But as far as interpretation of these results is concerned, if in fact the true model has a multiplicative error, and yet we estimate a model with an additive error, then you're able to show that that additive error will exhibit heteroscedasticity. And I think what's happening here is that probably the best model is one with multiplicative error, which does represent the fact that if we didn't have the multiplicative error, we would expect heteroscedasticity, which is a common feature of cross-section studies. In order to adjust for that heteroscedasticity, we take a variance stabilizing transformation. The log transformation is one of the well-known variance stabilizing log transformations. That gives us the multiplicative error specification. When we do recognize that heteroscedasticity in the cross-section and introduce the log transformation to get the multiplicative error, which helps to allow for the heteroscedasticity, the labor variable can be man-hours. However, if we don't introduce the log transformation of the model and use an additive error, then because the industries really are different, we need the hours of work variable, in effect, as a dummy variable to distinguish the different effects of the different industries. Remember that these are 24 very different industries, and we're assuming that they have a common production structure, which is likely to be an invalid assumption. In order to represent the differences between industries, we could either say that there's heteroscedasticity in the error, or alternatively introduce a dummy variable into the model for representation of the differences between the industries. In fact, when you look at the series for the hours of work, that does differ greatly between the industries. And that, I argue, is in fact acting as a dummy variable to distinguish the differences within or between the different industries. So that either of those representations should be acceptable. The multiplicative error approaches the problem of differences between the industry via heteroscedasticity. The additive error does it by using a dummy variable, and that dummy variable is the hours of work. And so if that argument is true, in practice it's not surprising that using these criteria we have difficulty in getting a strong preference for either the additive or the multiplicative error specification. Another interesting feature of the results would be to remember the result for linear models that a test statistic based on the Wald principle is going to be no less than the test statistic based on the likelihood ratio principle, which in turn will be no less than the test statistic of the same hypothesis based on the Lagrange multiplier principle. This has been established for normal linear models with general linear restrictions. For my particular application, I was all the time estimating, apart from the Cobb-Douglas function with multiplicative error, nonlinear regression models. An equality of this form hasn't been established for nonlinear regression problems. And in fact, it probably is impossible to establish an equality of that form for general nonlinear models. However, it was interesting in practice to compare the test statistics based on the Wald and likelihood ratio principles. I never computed a Lagrange multiplier test statistic. And in comparing the test statistics on the two principles, I found that there were cases where this inequality was reversed. Not many, but a few cases where it was reversed. But the important point was that when they were reversed, the decisions were never inconsistent. So if the Wald test statistic was rejecting the restrictions, then so was the likelihood ratio, despite the fact that this inequality had gone the other way. Finally, remembering that this was an exercise in nonlinear inference and nonlinear estimation, there are a number of computational points concerned with the nonlinear estimation of these particular functions. And first of all, if we consider a simple CES production function, only considering labour and capital, then we know for that representation the parameters A, alpha, and beta are not identified. So we need to impose some restriction. The usual restriction is to say that the sum of alpha and beta should be unity. So that the usual form of the CES function is in fact A delta n to the row plus 1 minus delta k to the row nu over O. And this has been introduced to identify the parameter. But as a consequence, we need to restrict delta to be between 0 and 1. And in fact, in some of my early estimation of CES functions, where I specified the model in this form and didn't impose this restriction, I was finding that the numerical optimization techniques were getting into ranges where delta was negative. And when you look at the value of the residual sum of squares for those negative deltas, they were very much less than other forms of the model with deltas positive. So that at that stage it became important to impose this restriction. If we're going to impose that restriction, then we could do that by transforming the problem and say that delta is in fact the sine squared of a new parameter, phi. We now know that sine squared of phi is always positive and never greater than unity. Therefore, delta will now satisfy this constraint. So at that stage, we would have to minimize the residual sum of squares for this function with respect to a, rho, nu, and phi. Once we've got phi, we can then solve backwards for delta. However, we would also be interested in testing hypotheses about delta. So we'd have to work out the asymptotic standard error of delta. And given the sine squared transformation, that complicates the computation of the asymptotic standard error of delta. So that rather than do that, the models that I estimated removed the capital A scale factor at the front, or alternatively set it equal to unity, and estimated models of the form Q is equal to alpha n to the power rho, beta k to the power rho, nu upon rho. So we've now identified alpha and beta by removing capital A. But we still have a problem that we require both alpha and beta to be non-negative. And again, we can impose that restriction by transformation. And the easiest transformation here is to square both alpha and beta. So that, if you like, alpha star, which is alpha squared, is always non-negative. Well, that's a simple transformation to impose the restriction, but it does result in a possible problem, in that there are two solutions for alpha for a particular alpha star. So there's the negative solution and the positive solution. So that when you're using the numerical optimization technique to get the minimum of the residual sum of squares with respect to alpha, you have to be careful in the choice of step lengths. In other words, the perturbations you consider on the parameters from the particular point you're at any one iteration. Because if that step length becomes too large, you can move from, say, the values of alpha in the region of the negative root over to the values of alpha close to the positive root. And you can just end up cycling between the negative and positive solutions. So that's still a problem with that transformation of the original specification. But provided you're careful in the choice of step length, you can avoid that. In the literature on transformations to remove or take account of restrictions, you'll also find that you could get an alpha star which is always non-negative by taking the exponential of alpha. And the reason why I preferred alpha squared to the exponential alpha is that in terms of computing time, it's much easier to compute the square than it is the exponential. The second computational point concerns the sequential testing. And although the important point about the optimal sequential procedure for testing is that you should start from the most general model and move successively to more restricted models. As far as the computation is concerned, if in fact you're going to perform the test statistics on the likelihood ratio principle, so that it's necessary to estimate the model corresponding to every hypothesis, as far as the computation is concerned, it's usually much better to do the computation in the reverse order. So that in testing, we move from the most general model to the most restricted. And that corresponds to the Anderson optimal procedure. As far as estimation is concerned, it's going to be preferable to move from the most restricted to the most general. And why does that come about? Well, it certainly doesn't apply for linear models. If the model you're estimating is linear, then the estimation problem is a simple one. Because if you're estimating the parameters by minimizing the residual sum of squares, the residual sum of squares are quadratic in the parameters, so that the first order conditions are linear in the estimators, and it's easy to get the solutions. However, when you come to problems which involve nonlinear estimation, then though for all the testing you need to have the global maximum for the likelihood function, or equivalently the global minimum of the residual sum of squares function with respect to the parameters on a particular hypothesis, in practice it's very difficult to ensure that you've got the global minimum. And in fact, you can often find situations where if you've estimated the completely unrestricted model and got a value for the residual sum of squares, so that's the completely unrestricted model, the most general model, you've then, at the other end of the scale, estimated the most restricted model, where in fact the residual sum of squares that you've got for the restricted model is less than the residual sum of squares for the unrestricted model. Theoretically, we know that that's impossible, but computationally, it can and does happen. If that does happen, then if you were to compute the chi-squared test statistics, you would find you've got negative chi-squared test statistics, which again is an indication that you haven't got the global optima in estimation. And by estimating from the most restricted to the most general, you can ensure that you never get results like that. So that you set off by estimating the model corresponding to the most restricted hypothesis. And you get a baseline for residual sums of squares. You then estimate the next less restricted hypothesis in the sequence. And you know now that you require the residual sum of squares for that model to be no greater than the residual sum of squares you got previously. In order to achieve that, you can use the final values of the parameters obtained in estimating the most restricted model as initial values for the iterative estimation of the next less restricted model. And for the additional parameter, if that's what's happening, you can put in the value of that additional parameter on the hypothesis corresponding to the restricted model. If you then, at that first iteration, compute the value of the residual sum of squares, it should be identical to the one you got previously. If then your numerical optimization routine ensures that you never accept parameter values for an increased residual sum of squares, it means that in the end, when you accept convergence, the residual sum of squares can be no larger than the one for the restricted model. And that goes on all the way through the sequence of models. So that by reversing the order of estimation, you can ensure that the residual sum of squares form a decreasing sequence as you relax restrictions, which we know theoretically must be true, though in practice needn't be true. Well, that completes my discussion of the production function application of model selection procedures. The next topic is to complete the discussion of statistical techniques for model selection before moving on to the time series problems. And the next technique I want to consider is that of simultaneous confidence intervals. And a reference here would be Shefay analysis of variance. So we'll return again to the linear regression model, but just for variety this time, let's introduce the null hypothesis, which is composite, which is R beta should be equal to small b. So general linear restrictions on the betas. And as before, if H0 is the only hypothesis we're interested in relative to the maintained unrestricted model, then the efficient test statistic of H0 is in fact the F-test, which we've had previously, which we could get either via the Wald principle, and so get the unrestricted estimates of beta, which would be the ordinary least squares estimates, and then compute the statistic divided by sigma squared. So that's the test statistic of the hypothesis H0, and that would be distributed as a chi-squared with degrees of freedom R when the number of restrictions we have in H0 is R. So that the R matrix is an R by K dimensional matrix. The F-test statistic is then obtained in terms of the Wald test statistic by multiplying by T minus K, dividing by R, multiplying by sigma squared, and dividing by the residual sum of squares, when M, as in all situations previously, is the idempotent matrix I minus x, x prime x inverse x prime. So this is just the unrestricted residual sum of squares. And that is distributed as F with R and T minus K degrees of freedom. And this is yet another way of writing this same test statistic, which I've put on the board many times in the lectures. And if all we're interested in is H0, then this is the efficient test statistic. However, if we are in fact interested in individual restrictions which form this composite set of restrictions, then we might want to consider tests which do look at the individual restrictions. And in particular, if when we perform this test, H0 was rejected, we might then want to find out which, if any, of these individual restrictions was causing the rejection. If that's the case, then we might now consider arbitrary linear combinations of those restrictions. So we can now consider a new hypothesis, H of A, which is A prime R beta minus B is equal to 0. And in particular, if we chose A to be 1, 0, 0, 0, all zeros apart from the first element, then what we're saying here is that we want to test the first restriction in this set of restrictions. So that would be an example. And this is where we come to a distinction between Bonferroni approaches to this problem and simultaneous confidence interval approaches. In the simultaneous confidence interval approach, we now consider hypotheses H of A for all possible A, provided A is non-zero. In other words, we're not only going to consider A's which are vectors of this type. This particular A pulls out the first restriction. If we had a second A, which was 0, 1, and then zeros everywhere else, that would pull out the second restriction. We're not restricting ourselves to A's of that type, which mean that we're concentrating on the individual restrictions in that set of restrictions. We're now allowing for the possibility that the A gives us some linear combination of that set of restrictions. And if we now want to test whether a particular linear combination of the set of restrictions which form our H0 is significant or not, what is the appropriate test statistic? Well, we can denote that by f of A. And that test statistic would now be A prime R beta hat minus B into sigma hat squared A prime R x prime x inverse R prime A, all inverse, and then R beta hat minus B prime A. And notice that by taking this linear combination of the original R restrictions, we are in fact now getting a scalar here, so that we would expect we could perform a test of that restriction using a t-test. And in fact, this test statistic is just the square of the t-test for that restriction. And in fact, is distributed as f with 1 and t minus k degrees of freedom on the null hypothesis HA. So that we could now, for all possible A's, set up rejection regions for h of A, how does that relate to an overall test of h naught? Well, a rejection region for h naught would be f of A, the test statistic we've got here, for this particular linear combination of the restrictions, greater than or equal to the critical value for, let's denote the critical value by C, from the F distribution for all A not equal to 0, when C is chosen to satisfy the probability that f of A is less than C for all A non-zero, given that h naught is true, is equal to 1 minus alpha. And the interpretation here is that this is the probability that simultaneously all the f of A's are less than C, when C is the critical value from the F distribution at significance level alpha. So that via these f of A's we can perform a test of H0, and this is the basis of that test. But what we require there is that all the f of A's simultaneously, in other words, for all values of A, should be less than C. If that's true, then it must be true that the maximum over A of f of A is less than C. If all f of A's are simultaneously less than C, then the maximum f of A must also be less than C. And this gives us a basis for performing the test using the maximal route. In order to perform that test, we want to know what the maximum of f of A is with respect to A. Well, unfortunately, I just rubbed out f of A, but f of A is A prime R beta hat minus B into sigma hat squared R x prime x inverse R prime inverse R beta hat minus B A. We now want to maximize that with respect to A. Well, that problem, or f of A, is really of the form A prime A on A prime B A. So it's really of the form of the ratio of two quadratic forms. So that in order to maximize that expression, we need to impose some normalization. And the usual normalization in that context is that A prime B A is equal to unity. If we translate back from this general situation to our particular one, that means that this inverse we would now normalize to be unity. So we can set ourselves the problem, maximize f of A subject to the restriction that what I've circled there is equal to unity. So that the Lagrangian expression would be f of A minus lambda sigma hat squared R x prime x inverse R prime at this stage I ought to correct the expression I had previously. everything in this square bracket is in fact the variance of this scalar. And it should be pre-multiplied by A and post-multiplied by A. I certainly missed it out in that expression. If I missed it out previously, it should also be in. So that we want that restriction. And if you look at the first order conditions for maximizing f of A subject to this restriction, you find that they imply R beta hat minus B into R beta hat minus B transpose A minus lambda sigma hat squared R x prime x inverse R prime A should be equal to 0. And we can now recognize that to be of the form a matrix into A equals 0. In other words, linear homogeneous equations. So if we want a non-trivial solution for A, then we require this determinant to be 0, or the matrix to have less than 4 rank. Well, if you look at this particular matrix, in fact, it's got a rank of 1. And so if we now solve the characteristic equation for the lambdas, for the roots, there's in fact only one non-zero root. And that non-zero root is obviously the largest, and in fact is equal to the trace of the matrix. So the largest root, the one non-zero root, is equal to the trace of that. If you rearrange that expression, you find, using the properties of the trace, you find that that expression is in fact R beta hat minus B transpose into sigma hat squared R R prime R beta minus B. And what is that? Well, if you look at the form of that, that is R times the statistic, which is an F with R and T minus K degrees of freedom. Namely, the F statistic for testing H0. R times the statistic we use for testing H0. Also, from the properties of maximization problems of this type, this largest root, lambda, does in fact give us the maximal value for the function we're trying to maximize, subject to the normalization constraint. So that the maximum of f of A over A is in fact that largest root, lambda, which we've just seen is equal to R times the statistic, which had R and T minus K degrees of freedom in the F distribution. Therefore, because of this previous result, we know we can perform this simultaneous testing at significance level alpha by testing on the maximal value of f of A. The maximal value of f of A is this largest root, lambda, and that is equal to R times the statistic, which has this distribution. Therefore, the test of H0 at significance level alpha has a rejection region which is max over A f of A greater or equal to R times the f R t minus k. So that under H0, when H0 is true, the probability is 1 minus alpha that f of A will be less than R times f R t minus k at significance level alpha. That will be satisfied simultaneously for all A non-zero. So the result we have is that when H0 is true, we've got a probability of 1 minus alpha that f of A will be less than R times the test statistic which we would compute for the direct test of H0 at significance level alpha simultaneously for all A. And this follows from these two results, that one and that. Therefore, the alpha level direct f-test of H0 will not reject H0 if and only if f of A is less than R times f at R and t minus k degrees of freedom for all A. That's probably worth writing down. Not reject H0 if and only if f of A is less than R f R t minus k at alpha for all A non-zero. So what is the simultaneous confidence interval procedure? Often called the S procedure or S method after Sheffe. Well, first of all, choose H0 and alpha, your significance level. Secondly, test any HA. In other words, choose any linear combination of the restrictions of the form A prime R beta minus B equals 0 using the statistic f of A and comparing it with the critical value from R times the critical value of the F distribution at significance level alpha with R and T minus K degrees of freedom. And the important point is that you can do that for any A. And if you do it for any A and any number, as many as you like, you can be assured that the significance level of the test implied of H0 remains alpha. So in this, you're testing any possible linear combination of the restrictions using the critical values from the F distribution with R and T minus K degrees of freedom multiplied by R at the alpha significance level. And despite the fact that you may do a very large number of these tests, the significance level for the test implied of H0 remains at alpha. Well, how does that now compare with a more conventional approach? Well, in a more conventional approach, we would probably do the direct F-test of H0. If that was rejected, we might follow that up by individual t-tests on individual restrictions. And what this analysis shows is that if we do reject H0 using the direct F-test, then it needn't be true that any one of the individual restrictions, whereby an individual restriction, I mean Ri beta minus Br is 0, where this is just taking from the full matrix R the ith row, and from the vector B the ith element. So that's just the ith restriction. Despite the fact that H0 has been rejected by the direct test, it needn't be true that any one of these restrictions, when you perform the test of significance, will be rejected. It might be, but it needn't. And that comes about because it's any A and any linear combination of the restrictions. So that in this, we're not restricting ourselves only to forms of A which pull out individual restrictions. It can be some particular linear combination of these individual restrictions that is rejected in the sample. So that, in fact, again highlights the difference between a conventional approach, where once H0 is rejected, your interest has been in the individual restrictions, so you go back and test each separately. And this simultaneous confidence interval approach, where in fact, even if H0 was rejected, it needn't be true that any one of these is inconsistent with the sample. What about the significance levels of the conventional approach as opposed to the significance levels for the S method? Well, for the conventional approach, once H0 has been rejected, we would, if we were doing individual t-tests or f-tests with 1 degree of freedom on individual restrictions, taking the critical values from the F distribution with 1 and T minus K degrees of freedom at, say, the alpha level. And that's for the conventional testing. We're now looking at these separately. In the S method, we will be taking the critical values from R times the critical value from an F distribution with R and T minus K degrees of freedom, which obviously is larger than the critical value from the conventional method. So this is with the S method. If we now notice that we can, by changing the significance level, get an equivalent critical value to that, in particular, we can find an alpha star such that the critical value from an F with 1 and T minus K degrees of freedom is equal to the critical value for an F with R and T minus K at alpha degrees of freedom. Then we notice that alpha star must, in that situation, be less than alpha. So that this test statistic now is in a form comparable with the one for the conventional approach. They've both got the same degrees of freedom, but the significance levels are smaller for the S method. As a consequence of that, the confidence intervals on parameters are larger for the S method than they would be for the conventional approach. And in fact, that's one of the major criticisms leveled against the simultaneous confidence interval approach, that the intervals are far too large for most practical problems. But you can't make that statement independently of the statement that, in fact, there are only a subset of the linear combinations of the restrictions that you're interested in. If you were genuinely interested in all possible linear combinations, then you should certainly use the S method. But if in your particular situation are able to specify certain of the restrictions or certain linear combinations of the restrictions which are of interest to you, then a more conventional approach is likely to be preferable to the S method in the sense that the confidence intervals are going to be smaller, or equivalently that the significance levels implied would be larger. And that particular observation leads in directly to the Bonferroni intervals. In fact, in the Bonferroni intervals, you specify the set of restrictions that you're interested in. So we could be testing H0, which is a composite, but we have said that we are in fact interested in the individual restrictions as well. And in the context of a linear regression model with the exact linear restrictions, if we were looking at the ith restriction, then the test statistic we could denote by tau I, which is Ri prime beta hat minus Bi upon its standard error. In other words, that's just on the null hypothesis distributed as students T with T minus K degrees of freedom. And we would also have to specify a significance level for each of the tests. So for the ith test, we've got a size of epsilon I, or probability of type 1 error of epsilon I. And that would be our test statistic for Hi, which is Ri beta minus Bi is equal to 0. Well, one possible procedure is now to accept H0. Remember that H0 is the full matrix R, beta minus B equal to 0. We accept H0 if and only if none of these individual restrictions are rejected. And that would be perhaps a reasonable procedure. However, these test statistics, tau I, are not in general independent. So that if we perform each of these tests at significance levels epsilon I, we have to work out what the implied significance level is for the test of H0. Given that these individual tests are not independent, that's quite a complicated problem in general. And in fact, that was one of the beauties of the ordered sequential testing of Anderson that the individual tests were independent, and so it was easy to calculate what the implied significance level was for the test of H0. But in general, they're not independent. And the essence of the Bonferroni approach is to set your intervals, or rejection regions, by just taking the probability of disjunction for these tests, ignoring the conjunction. And what do I mean by that? Well, if we look at the probability that the absolute value of the statistic tau 1 is larger than the critical value epsilon 1 upon 2. These are two-sided tests at t minus k, that tau 2 is larger than t at epsilon 2, t minus k, and so on to tau r is larger than t minus k epsilon r upon 2. Given that H0 is in fact true, then that is the probability of type 1 error in the testing of H0, given our procedure that we would reject H0 if any one of these test statistics was significant. So we need to evaluate that probability. The difficulty in evaluating it is that these test statistics are not independent. And in fact, what we have to evaluate here is the probability of a union of a number of different events. But we know that the probability of the union is in fact equal to the sum of the separate probabilities minus the probability of the conjunction of all those events. So that we could approximate that probability by ignoring the probability of the conjunction and just approximate it by taking the sum of the individual probabilities. And what that would be is the sum, I is 1 to r, of the probabilities of type 1 error for each individual test. Probability of type 1 error involved in the first test is epsilon 1. If we add to that the probability of type 1 error on the second test, we add on epsilon 2, and so on through to the epsilon r for the rth test. But we know, because this is in fact the union of those events, that the probability of a union is equal to the sum of the individual probabilities, or the marginal probabilities, minus the probability of their jointly occurring. We're going to ignore that. Therefore, this expression must be greater than or equal to the actual probability of type 1 error. Which completes the outline of the Bonferroni intervals. At the beginning of the next lecture, I'll briefly give an interpretation of that and then go on to the time series applications.